If I was to ask you if computers have become progressively smaller throughout history, you would probably answer yes. But the truth is, there was a period of about 100 years in the early history of computers where they only got larger. One of the largest was the ENIAC, which weighed 30 tons and filled up around 1,800 square feet of floor space, the size of the average Australian house. It started operating in 1943, and it was estimated that in its 10 years of running, it pumped out more calculations than the combined efforts of the whole of humanity up to that point in history. So how did we get from computers that could fill a small building to a computer even faster than that one that fits in your pocket? Well, the answer is transistors. Without this key breakthrough, the internet would not exist. When we ended last episode, we had just finished talking about Herman Hollerith's electronic tabulating system and its groundbreaking results. And a brief, fresh discussion of his system will help us lay the groundwork for the introduction of transistors and why they were so important. Hollerith's system is what we would call an electromechanical system, this meaning it combined both electronic and mechanical elements. This can be most easily seen in the switches we discussed last episode, where when a current is initiated, an electromagnet is activated that moves a metallic switch into an on or off position, either allowing or cutting off a flow of current. There are two very obvious limitations to this system. Firstly, there is a built-in limit on speed because there is a finite number of times that switch can be activated per second. Secondly, is mechanical systems fall prey easily to wear and tear. Switches, joins and gears wear out and are therefore prone to failure. And when you're dealing with incredibly complex systems involving thousands and thousands of moving parts, it was common for failures to occur daily, then involving very complex and intricate repairs. One such example was when a moth found its way into the massive Harvard Mark II computer and died, causing a fault in the system. The world's first computer bug was literally a bug. The speed limitations found in the current process were the first to be overcome, with the implementation of the vacuum tube. Now, the vacuum tube had already been in existence since 1904, when the British engineer John Ambrose Fleming invented the thermionic valve, building on the work of William Crookes and his Crookes tube that we discussed a couple episodes ago. And it became one of the most important breakthroughs in the advance of many electronic mediums, including radio, television, see the cathode ray tube discussed in previous episodes, radar, sound recording, long-distance telephones, and most importantly in our case, computers. Much like the cathode ray tube, this was a glass tube containing a vacuum and a cathode and an anode, between which electrons would flow at an incredibly high speed. And in this case, the electrons were emitted by a heated filament. But this is not yet a switch, so it's still not useful when it comes to replacing electromechanical switches that were in use. In 1906, American Lee DeForest added a third element, a control grid, that could be used to switch the flow of electrons on or off by alternating between a positive or negative charge. This now allowed the vacuum tube to operate as a switch, and crucially as a switch that contained no mechanical parts, and so could now operate thousands of times per second. One of the first major computers to make use of the vacuum tube was the Colossus, used to break German ciphers during World War II, with the Colossus Mark II using 2,400 vacuum tubes in its operations. Data would be input via tape with punched holes, and at its fastest, it was capable of processing 25,000 characters per second. But we were still butting up against the limitations of wear and tear, as these tubes were fragile and the filaments could burn out. The enormous ENIAC utilized over 18,000 tubes, with on average a tube failing every 2 days, requiring the failed tube to be found and replaced. There was also the obvious limitation of size too. A vacuum tube had a limit on how small it could be made, and at the sheer numbers required, both the cost and size leaves us with a huge gap between the ENIAC and the modern computer. But that gap became suddenly significantly smaller when 2 years after the ENIAC had been completed, the first transistor was invented by physicists John Bardeen, Walter Brattain, and William Shockley in 1947. The key breakthrough was the use of a material called a semiconductor. This means a material that can switch between a conductive and a non-conductive state when a charge is applied, meaning it can switch between allowing current through or blocking it incredibly fast. Already you can see how this can work very effectively as a switch, and they are way more sturdy than the fragile vacuum tube, last way longer, and can be made to be way smaller. However, this approach was soon blown away by the invention of integrated circuits, which completely changed the process for everyone. Silicon had been found to be the ideal semiconductor to be used in transistors, and with it just so happening to also be the second most abundant element in the Earth's crust, it meant that the material for manufacturing transistors was widely available and therefore far cheaper than the costs of manufacturing vacuum tubes. And it was eventually discovered that a single block of crystalline silicon could be treated to grow multiple transistors with the wiring already in place. This opened the door to an incredible acceleration both in the power of computing and also a rapid reduction in size, to the point today where we have the Apple M1 Ultra chip that comfortably fits inside a small desktop computer and contains 114 billion transistors. When you consider that the ENIAC had the equivalent of 18,000 transistors and was the size of a house, you realize we've come a long way, and you begin to understand how much of a game changer the transistor was. So we've now got computers that are able to be much smaller and much more powerful, containing billions of tiny switches capable of switching an impossible number of times per second. The fastest ever made, capable of hitting a frequency of 600 billion times per second. But how is that even useful? Well, we'll get into that next episode when we discuss binary and all its wonderful ones and zeros, and get into the incredible world of possibilities that was opened up by a signal so simple.